there, science. This is Miss Satterley. I'm going to talk about our notes that we have on plate tectonics. Okay, plate tectonics is a theory that pieces of Earth's lithosphere, called plates, move slowly on top of the ionosphere, which is the second layer of the mantle. And this can explain the formation and movements of plates. Now, again, our lithosphere, which is in the first section of notes, includes both the Earth's crust and the upper part of the mantle. Now, Alfred Wegener was a scientist who proposed a hypothesis called continental drift, and also came up with the concept of the supercontinent called Pangaea. And he did his main work in 1912. So continental drift, what actually is that? Continental drift says that continents move slowly across Earth's surface. This can help explain why continents seem to fit together and why also fossils of the same organism are scattered across the globe. There are actually fossils that are on the east coast of South America that are very similar to fossils found on the west coast of Africa. And that's because it's thought that South America and Africa once used to be joined together and drifted slowly apart through continental drift. So what is Pangaea? Pangaea is the ancient supercontinent. This is when all of the continents that we have now were all joined together in one. It means all land. So eventually it broke apart into pieces due to continental drift. Now, Harry Hess is another scientist that I want to talk about, and he did his main work in 1960. He was an American geologist, and he proposed the theory of seafloor spreading. So I had you guys watch several videos talking about plate tectonics, continental drift, and seafloor spreading, just so you could see a little bit of a visual and help add to our lesson that we have with this. So what is seafloor spreading? Seafloor spreading is the process by which new oceanic crust is created at mid-ocean ridges as older crust moves away. So mid-ocean ridges are found under the ocean, and this is where there's actually a crack between the plates where magma is able to reach the surface and causes things to be spread apart. So the mid-ocean ridge is a chain of underwater mountains. One of the major places that we have a very large chain of mid-ocean ridge is actually right in the middle of the Atlantic Ocean. It's the world's longest mountain range located there, and it's a huge crack in the crust where magma pushes upward. Now, subduction also happens because of this process underneath the ocean. Subduction is when an oceanic plate is sinking into the mantle. Now, sometimes you can actually have two oceanic plates that go through subduction, or sometimes you have a subduction zone where it's one oceanic and one continental. This occurs near the edges of oceanic plates, and we call these places subduction zones. So they actually, the one plate will go underneath, it will be heated up, and it becomes molten magma again. And then over time, that material is going to be recycled and then pushed up again through the mid-ocean ridge. So how does subduction work? Oceanic plates move away from mid-ocean ridge. It cools and becomes more dense. The force of gravity is to pull the dense edge into the mantle, and it's going to destroy the old sea floor. One end of a plate, we're going to have the mid-ocean ridge, or a place where magma comes up. The other side, we're going to have a trench. A trench is a depression in the ocean floor, and this is caused by the bending of a plate that sinks into a subduction zone. So the Mariana Trench it's the deepest place in the ocean. It is 7 miles deep at its deepest spot. They have not really explored the Mariana Trench very much because of the extreme pressures down there. There are creatures down there. They have done a couple voyages. It is named the Challenger Deep after the voyage ship, the HMS Challenger, was actually the one that discovered the Mariana Trench. That's just a little background about that. Seafloor spreading and subduction. So it acts like a conveyor belt. So seafloor spreading is going to create new oceanic crust at the mid-ocean ridge, but subduction is going to do the destroying of the old oceanic crust at subduction zones. So that's a conveyor belt. It's constantly being recycled. There's also some evidence of seafloor spreading that's on the bottom of the ocean, and these are called magnetic stripe patterns. They're also nicknamed zebra stripes. They're caused by Earth's magnetic field. Reversal of the magnetic field direction actually is going to cause the crystals in the hot magma to align with the magnetic field. Stripes form. And every about 11 years, Earth's magnetic field is actually going to reverse itself. So underneath the ocean, after that 11 years passes by, the next rock is going to align the opposite direction, and it actually causes a very distinct banding pattern that's visible at the mid-ocean ridge. Floor is added on both sides of the trench, so you actually can see the pattern on both sides. Rocks that are near the ridge are going to be younger, while older rocks are farther away. So let's get into the theory of plate tectonics in a little more detail, now that we've had a little background information about some of the processes. So the theory of plate tectonics is a very new science. It was developed during the 1960s. Earth's plates are constantly moving at different rates and different directions, and that's what causes the continents to drift apart. Now, some of them might be drifting apart, but some of them are also getting close together, and eventually they might join together over a long period of geologic time. Now, plate motion is a visible part of mantle convection. The plate motion that we see is due to the mid-ocean ridge and also the subduction zones. Mantle convection currents. A convection current is going to be a loop of energy that forms. We also have convection currents on the sun. It forms at mid-ocean ridge. A rock cools and spreads and then sinks into the mantle at subduction zones. So down here, hot air rises. So that's why the magma is going to actually rise to the surface, because it's very hot. And then the cooler crust is going to sink, and that's how the convection current happens. Now, there are actually two sources of heat within our interior. One is the gradual cooling of Earth's interior. So when Earth was formed, it was a hot, molten ball of magma. It's been slowly getting cooler over time, but it hasn't cooled off entirely, and that's because we have the decay of radioactive isotopes. And when radioactive isotopes, there are 7 major tectonic plates. 12 is actually going to include some of the medium-sized one as well, and they meet at plate boundaries. There are 3 different types of boundaries: convergent, divergent, and transform. We're going to talk about the characteristics of each one of those boundaries. Down at the bottom, I actually have a fact here. Plates move very slow, about 0.1 to 10 centimeters per year, and that is actually about the same rate that your fingernails will grow. So the first one is a divergent boundary. Divergent boundaries are where plates move away from one another. Plates are going to move apart, and magma will rise from the mantle to fill the gap. Magma cools, forming new rock at the plate edge. An example of a divergent boundary is going to be the mid-ocean ridge. Our next one is the convergent boundary. Convergent boundaries are when plates come together or collide. The oceanic plate that's subducted beneath the trench is an example of a convergent boundary. Denser oceanic plates are going to slide underneath less dense continental crust, and that is a convergent, where 2 different plates are joining together. Now, our next one is a transform boundary. Transform boundaries are when plates slide past one another. They're going to move in opposite directions. Rock is neither created nor destroyed at a transform boundary, and the most famous transform boundary is actually the San Andreas Fault. So, mountain building. Mountain building is going to form along plate boundaries. At a convergent boundary, you're going to have 2 continental plates that collide, which is going to cause the crust to be pushed upward. There's no subduction when you have this case. And an example of a mountain formation that forms at a convergent boundary is the Himalayas. Himalayas is actually formed where the Indo-Australian plate is crashing into the Eurasian plate. Oceanic plates will collide with the continental plate, pushing up the crust. And that's another example of a convergent boundary. The example of that is the Andes Mountains. The Andes Mountains is formed from the Nazca Plate and the South American Plate colliding. Now, divergent boundaries are not going to form mountains. They're going to form ridges underneath, and that's from the magma being pushed upward. All right, that is our last slide for today. I hope that was also helpful. I hope you have watched the YouTube videos that I wanted you to watch and filled out the questions. And me talking about it after you watching that, I hope that reinforces all the concepts in this. So we will have a quiz on this. We're going to save the quiz for next week. I will have a Google Form homework assignment. A couple more things that I want to go over. I do want to go over the different types of tectonic plates, so I want you to be able to identify those as well. So that's another thing we have to do as well. Okay, so if you have any questions, please let me know. Have a wonderful day. Bye.